Initial quote today is: most marine sediments are derived from the weathering of rock on land by the action of wind, water, and ice under the influence of temperature, pressure, and chemical reactions. And here is another quote. Although sediment type and input depend on geology, they are strongly influenced by climate. Climate directly affects the rate at which rocks are altered physically and chemically to eventually liberate sediments and indirectly influences the transport of these to the coast. This map illustrates the distribution of the total sediment thickness of the world's ocean and marginal seas. In gray are the continents. In white is no information. The color scale represents the sediment thickness in meters, ranging from almost zero in the dark blue up to 20,000 meters in dark red. It is important to see that the thickness is huge over the continental shelves and reflects those materials from terrestrial origins. Those arrows point to the thickest deposits. They illustrate that rivers like the Mississippi in North America, the Amazon in South America, and the Ganges River in Southeastern Asia are among the most contributive rivers for the world's coast. From the coast to the deeper ocean, sediment thickness gradually reduces. On the deepest seas, sediment thickness is almost negligible, like on the abyssal plains, and reflects slow depositional contributions mostly from biogenic materials. This map presents the global distribution of 40 deltas in the world, showing the potentially contributing drainage basin area of each delta in blue and the large reservoirs in each basin. Human impacts on coastal sediment supply date back to ancient times, essentially through modification of river catchments via agriculture and land use. Also through river damming and through the development of coastal settlements and activities. However, separating the human contribution to the perturbation of coastal sediment budgets from natural parameters is difficult. Changes in land use and agricultural practice have been shown to cause fluctuations in sediment supply from river catchments. Sediment sequestering in dams is a worldwide phenomenon. There is a likelihood that the goals of sustained economic development in many developing countries where population increases are set to continue will involve more important dam constructions in the future, thus significantly impacting many deltas and therefore the sediment supply to coasts. Some authors have suggested that humans have simultaneously increased the sediment transport by global rivers through soil erosion and yet reduced the flux of sediment reaching the world's coastline because of the retention within the reservoirs. Over 100 billion metric tons of sediment are now sequestered in reservoirs, constructed largely within the past 50 years. For example, African and Asian rivers carry greatly reduced sediment loads than Indonesian rivers, which deliver much more sediment to coastal areas. So now let's talk about types of sediments. Lithogenous sediments, quartz and clay minerals, enter the sea as discrete particles, like boulders, stones, gravel, sand, silt, and clay. The hydrogenous sediments are formed by precipitation from seawater. Example, salt-type sediment and those manganese nodules. Biogenous are sediments that are formed by organisms. Example, coral and shell sands. Other quote is that from Professor Komar. Most beaches are composed of sediments derived from disintegration of the land. The composition of beach sediments reflects the nature of the source rocks and often can be used to access relative contributions and transport paths from the sources to the beaches. The igneous rocks, that are intrusive and extrusive magmatic rocks, are the original primary sources of sand worldwide. Sedimentary rocks are the secondary source of sand and can be divided in marine volcaniclastics, approximately 15%, continental pyroclastic, 2.6%, gray rocks, approximated 2.6%, arcals, approximately 5.3%, quartz sandstones, approximately 7.5%, mud rocks, approximately 60%, dolomites, approximately 0.7%, limestones, approximately 5.3%, and evaporites, approximately 1%. Although most sedimentary rocks incorporate variable amounts of the fine-grained matrix material, pyroclastics, sandstones, and limestones are the most prominent sedimentary sources of sand. Carbonate rocks have either been derived directly by precipitation of CaCO3 from water supersaturated in carbonate or by the accumulation of bioclastic material produced by marine organisms. Beach sands derived from unconsolidated or semi-consolidated terrestrial deposits or from sedimentary rocks have undergone several cycles of erosion, transportation, and deposition. This graph shows the longitudinal distribution of sediments and rocks on continental shelves with implications for beach sediment transport. Despite the considerable variability in the amount and type of sediment supplied to the world's coastal zones, there appears to be a distinct latitudinal trend in the shelf and nearshore sediments average composition. This trend should be reflected in the composition of beach sediments of adjacent coasts. Quartz sands have the greatest resistance to mechanical weathering, whereas feldspar are easily broken down into increasingly smaller fragments when exposed to mechanical forces because of their perfect cleavage. Consequently, quartz sands tend to be enriched relative to less resistant materials, especially in the course of prolonged fluvial transport. However, close to their source, even less resistant minerals may form dominant sedimentary components, for example, olivine on beaches of volcanic islands. Back to this graph, mud deposits predominate nearby the equatorial zone because of the higher temperatures and higher rainfall rates, and thus the weathering is more efficient than in the higher latitudes, where there is less weathering and rock and gravel predominates. In the mid latitudes, quartz sands are more predominant in coastal deposits. The source to sink approach shows that the original sediment supply occurs at several temporal and spatial scales, animated by short-term events such as extreme floods, storms, earthquakes, and volcanic eruptions, which may be superimposed on long-term tectonic and sea level trends, depending on the geophysical and climatic context of both the sediment supplying hinterland and the nature of the coast. Please take a closer and attentive look at this image. Fluvial sand supply. Worldwide, rivers supply about 90% of coastal sediments, and this amount have been estimated at 10 to 20 billion metric tons, with large uncertainties due to human intervention, like damming and sand mining on rivers. Cliff erosion accounts for only about 5% of sediment supplied to coasts, and this is significantly less important than fluvial supply. The retreat of soft rock cliffs may release sediment for in situ beach development over a shore platform or for transport along shore on beach sinks. Cliff erosion and retreat is commonly episodic, highly variable along shore, and related to a large variety of mass movements and failure events, such as block falls, debris flows, mud flows, rotational slumps, and slides. Longshore sediment transport enables the redistribution of sediment along the coast and may operate within the framework of one of several sediment cells with bounding limits to longshore drift. Seabed erosion. Sediment inherited from the inner continental shelf or shoreface from earlier sea level stands may be reworked by waves and currents to source beach and barrier coasts. It has long been recognized as a fundamental component of long-term coastal development. This diagram illustrates the coastal sediment tract across which occurs sediment sharing between the coast and the continental shelf at various time scales. Biological production. Bioclastic sand is produced by the breakdown of calcareous algae and shell-bearing organisms. Example, bivalves, gastropods, and barnacles, living in the intertidal, subtidal, and some deeper shelf environments. The breakdown products of such organisms have fed adjacent beaches across continental shelves from sea level low stand to modern high stand positions and are usually mixed to various degrees with terrigenous materials. Pure carbonate sands commonly line the shores of atolls and some other areas fringed by coral reefs. In the tropical and subtropical shores fringed by reefs, almost the entire beach material may be derived from the onshore transport of coral debris. Artificial nourishment. Artificial nourishment of beaches can be defined as the process of mechanically or hydraulically placing sand directly on an eroding shore to restore or form and subsequently maintain an adequate protective or desired recreational beach, or as deliberately placing an amount of sand on an eroding beach or creating a beach where no beach or a narrow one was present before. Boulders on the shore. Deposits of boulder-sized materials have drawn attention over the last few years, mainly within the framework of the debate revolving around whether the megaclasts are transported and deposited by storms or tsunamis. Boulders on beaches can also accumulate simply from in situ weathering of resistant bedrock. The role of ice in the transport and deposition of boulders may also be preponderant in cold climate areas. The image on the left shows a megaclass deposit, and the image on the right shows a boulder beach along the west coast of Ireland, County Clare. On several coasts of the world where such deposits occur, there is a debate as to whether they were deposited by storm waves or by tsunamis. Morphoscopy is the scientific examination of the shape of small particles. In 1953, Powers proposed a roundness scale of quartz sandy particles. The particles were classified by morphoscopic analysis as well-rounded, rounded, sub-rounded, sub-angular, angular, or very angular. Take a closer look at its differences. Granulometry is the measurement of size distribution in a collection of grains. Not all the sediment composing a beach is sand. Size classifications were developed to determine what qualifies as sand, what is gravel, and so on. One of the most adopted scale was made by Wentworth in 1922, which classifies sediment by size in millimeters based on powers of 2. This chart can be found at USGS website and is strongly based on Wentworth's scale. It presents the size terms, their scale in millimeters, their scale in phi unit, the sieve sizes, the number of grains per milligram, the settling velocity of quartz sands, and the threshold velocity for traction. At this moment, the important information is from the size of the grains. From the bottom to the top, clays range from 0.001 millimeters to 0.004 millimeters or 10 to 8 feet. Silts range from 0.004 millimeters to 0.062 millimeters or 8 to 4 feet. Sands range from 0.062 millimeters to 2 millimeters or 4 to minus 1 phi. Pebbles range from 2 millimeters to 64 millimeters or minus 1 to minus 6 phi. Cobbles range from 64 millimeters to 256 millimeters or minus 6 to minus 8 phi. Take a closer look at the USGS scale. To classify beach sands, it is necessary to determine their grain size distributions and associated textural parameters, such as mean, median or modal diameter, standard deviation or sorting, skewness, and kurtosis. The granulometry of sands based on Wentworth's 1922 scale shows us that sands can be subdivided into 5 classes: the very fine sand, the fine sand, the medium sand, the coarse sand, and the very coarse sand. Also, in this table, we can see some of their intervals using the millimeter scale and the phi scale. Note that phi values represent the negative binary logarithms of the millimeter scale. It's just another unit, an adimensional or non-dimensional unit used by sedimentologists over a long time. Phi scale inverts the millimeter scale, so where the higher is the millimeter, the lower is the phi value. Also in this table we can see the settling velocity in centimeters per second. It's supposed to be the velocity of grains under the water. Those results are experimental and are valid for quest spheres of specific density of 2.65. Granulometric analysis consists in determining the dimensions of the particles that constitute the samples, presumably representative of the sediments, and in the statistical treatment of this information. Basically, what needs to be done is to determine the dimensions of the individual particles and study their distribution, either by the weight of each dimensional class considered, either by its volume, or by the number of particles integrated in each class. There are many granulometric methods. I have chosen the 3 most used. By far, the most used method for granulometric analysis is the sieving analysis. It may have too many things to say about this method, but I have chosen some topics to simplify. First, the sample must be salt-free. Multiple washing is required. We use deionized water to wash the sample. In second place, the sample must be dry. It's used at a hothouse in temperature about 60 degrees Celsius after the washing process. Then the sample initial weight must be measured. Then the quartering. The quartering is the process to subdivide the sample in 2 and 4 parts just to guarantee that we have some aleatory selection of grains to the analysis. In some investigations, biogenous particles in the sample must be burned using sodium hypochlorite, and if so, a second weighting must be done. Sieves must be mounted usually using half-Phi intervals. Sieves must be shaken for about 15 minutes with the sample inside. Then is the weighing of the particles resting in each sieve. And finally, all measures must be annotated in a spreadsheet for further analysis. The settling analysis generates settling velocity distributions and, by transformation, equivalent settling diameter distributions of sand samples. The advantage of this procedure is that the particles' shape and density enter into the settling behavior besides the physical particle size. A major disadvantage is that settling tubes are not commercially available, and the few tubes in operation today are mostly in-house constructions. First, we subset 3 grams of each sample to be analyzed, then we film and time the operation, and then we determine the median settling velocity value using a spreadsheet. The third example of granulometric methods is the laser diffraction analysis. This is an optical method consisting of laser diffraction response when in contact with the grains. The physical principle is that the diffraction angle is inversely proportional to the particle dimensions. The sample must be preparated and subsetted to 10 grams. The equipment must be correctly set. SOP are the standard operating procedures regarding the output data needed. Granulometric scales. The first scales to be used were the most evident, arithmetic, as is the millimeter scale. It was found, however, that linear or arithmetic scales are not the most appropriate to obtain good results in the study of sediments. Indeed, when studying the particle size distribution of sediments using arithmetic scales, it appears that this distribution is systematically asymmetric, that is, most particles are concentrated in the smallest dimensions. In nature, most populations follow Gaussian distributions, also called normal distributions. If in the study of sedimentary particle populations, geometric scales are used instead of arithmetic scales, it appears that the resulting distributions are much closer to the Gaussian curves. For this reason, it has long been attempted to describe sediments based on geometric or logarithmic scales. In 1934, Cronbane used the exponents, powers of 2, of the Wentworth scale based on a logarithmic scale, which he designated as the phi scale. The main goal of this transformation was to facilitate the application of conventional statistical methods to sedimentology. This scale was widely accepted by the scientific community and is currently extremely popular. Histograms. The granulometric distribution visualization is critical in the sedimentological analysis since it allows us to have an immediate notion of the main characteristic of this distribution. Histograms are the simplest and easiest ways to represent particle size distributions. The lower values of phi, negative values corresponding to the larger particles, must be represented to the diagram's left. A column proportional to the percentage that this size has in the analyzed sample must be represented in each class. Throughout the 20th century, several descriptive measures of sediment granulometry have been proposed. However, as the granulometric distribution curve frequently approaches more or less the normal curve, Gaussian or Bell, the tendency to describe the granulometric curve based on the comparison with the Gaussian curve was manifested early on. Typically, 4 types of descriptive measures are used. The central tendency measures allow us to know whether, on average, the particles that make up a distribution are more or less coarse than those of another distribution. This is often related to the intensity of the transport agent and or the energy levels of the depositional environments. The most used parameters are the mode, the median size, the mean diameter, and the graphical mean. The mode represents in percentage terms the highest frequency of given grain size. The mean or average indicates the average size of the sediment, translating in terms of available energy the speed of depositional agent, and interpretation of source areas and energy of the transporting agent. Being more affected by the tail, it is more sensitive to the study of processes. The median is placed between the mode and the mean or average, between the value with the highest frequency of occurrence of a given size and the value obtained through a simple frequency graph. Considering central tendency measures, the median parameter best characterizes sedimentary deposits. Dispersion measures. Dispersion or uniformity measures, such as calibration, express the highest or lowest concentration of particles around the average. These measures often reflect the constancy or irregularity of energy levels. For us, The sorting that is related to the standard deviation is usually very useful. The standard deviation describes the dispersion concerning the mean and defines the degree of selection or sorting of a sediment sample. Look at this image. This figure shows that for the same mean or average, you can find different standard deviations. Let's see some examples. In blue, there is a lesser standard deviation and there is a best sorting. For example, a dune sample. In red, there is an intermediate sorting, example, short phase sample. And in green, there is a greater standard deviation or worse sorting, for example, a surf zone sample. Asymmetry measures. Measures of asymmetry of the curve, that is, of enrichment of the granulometric population in fines or courses, which cause deviations from the normal curve. These measures express the enrichment of the particle size distribution in coarse or fine particles, and then use the skewness. Those asymmetry measures of the frequency distribution and marks the mean's position concerning the median, describing whether the curve is symmetric or not. Being asymmetrical, it can lean the longest tail of the curve to the side of the thick or thin fractions and can be negative or positive respectively. Measures of curve's angle. Measurements of the angle of the curve, that is, the evaluation of the length of the tails of the curve in relation to the normal curve. In fact, they reflect the calibration of the curve tabs relative to the calibration of the central part of that curve, and then we use the kurtosis. The kurtosis is the measure of the distribution's curve slimness, comparing the selection between the central 90% of the curve with the central 50% of the curve. These parameters suggest some depositional trends when platykurtic, which may indicate a mixture of different populations, and transport trends when leptokurtic, which may indicate the removal of some fraction through bottom currents. Look at the example of the leptokurtic blue curve, the mesokurtic, that is an intermediate condition, and the red curve that represents the platykurtic condition. The bigger picture is that no overall parameter or combination of them is adequate to reveal all the properties of a complex frequency distribution. The entire curve must be seen to be appreciated, just as no anthropologist can adequately characterize a Brigitte Bardot by 4 measurements alone. Paul D. Komar. Let's practice. In this third exercise, you are supposed to search and download the GradStat spreadsheet built by Blott and Pye in 2001. Open it in Microsoft Excel and enable macros. Read some information about GradStat. Access the tab Single Sample Data Input and fill the data as in the examples of samples sent to your email today. Samples 1 and 2 are in half-Phi intervals. Samples 3 and 4 are in laser granulometer intervals. Press Calculate Statistics and use the information shown, including the histogram, to write a small report for each sample regarding the granulometric parameters. Tip: consider the resulting values in the Folk and Vard method in the logarithmic scale. Also, consider using the description given to write your report. Good luck! The simple report must be sent to my email address. Enough for today. See you soon. Take care and be safe.